Anyway, we are talking about power series, right? Power series, this is a series, but it's sort of turned into a polynomial by putting powers of x. So, you know, something like 1 plus 2x plus I'm already not liking this app. Well, that's all right. Like this is a power series with the dot dot dot. It's like a polynomial that goes on forever, right? We can write it as a series. I guess in this case, this series would look like n times x to the n minus 1. That's what that one looks like to me. But this is a power series, and it acts like a function, so you can call this f of x, and you can, if you want to, you can plug values in for x and see if you get an answer. Now, sometimes you will get an answer, but sometimes the series will diverge and you don't get an answer. So it's like a function, but sometimes it diverges. I'm going to say it this way. It's a function, but it only converges for certain values of x. And what I want to talk about today is, if I give you a power series, can you tell me for which x does the power series converge and for which x does it diverge? We did one example of that last time. I want to do a bunch more today. So it's a function, but it only converges for certain values of x. All right? This is the idea of a power series. Let's try one. I did one last time. Let me just, maybe I'll just say as a preface here, to find which x make it converge, we are usually going to use the ratio test. Right? The ratio test turns out to be very well suited to answering this question: for which x does a given power series converge? Here is an example. We did a simple example last time. Let's try a fancy example. There's actually, this is sort of a historically interesting example. This is called the Bessel function, and it has a very complicated looking power series expression, but it's not so hard to work with, but it does look complicated. F of x equals the sum, just for technical reasons, this sum starts at 0. It doesn't really matter, but if you want to get the Bessel function, you got to start the sum at 0. Anyway, it's this: minus 1 to the n, x to the power 2n, divided by 2 to the power 2n times n factorial squared. How you like that? N factorial squared. Remember the factorial, I don't know if we haven't talked about this much, but that exclamation point means n factorial. And the factorials actually occur pretty commonly in lots of important examples of power series, so we're going to be seeing more of the factorial as we go talking about power series. Anyway, n factorial, what it means is n factorial is it's n times, let me write it. I'm going to write it the other way around. It's 1 times 2 times 3 times etc. until you get up to n. This is called n factorial. We write it with that exclamation point, and it means you just multiply all the numbers up to and including n. So, for example, 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which is, whatever that is, this much was 6, and then times 4 would be 24, right? And so on. And one, just before we go any further with this, one important property of the factorial that we're going to use all the time is this: n factorial divided by n plus 1 factorial. You know, when you do the ratio test, you always end up with things like a bunch of things with n's and then comparing with, or in fractions, with things with n plus 1s, because that's how the ratio test is set up. N factorial divided by n plus 1 factorial. What is that? Well, on the top, what you have is the product of all the numbers up to n. And on the bottom, you have the product of all the numbers up to n plus 1. Well, in those products, like, all the stuff will cancel, right? Like, up, whoa, sorry. Okay. Sorry about that. Up top, we're going to have, 1 times 2 times 3 times up to n. And on the bottom, we got 1 times 2 times 3 up to n, and then also n plus 1, right? But what can you do there? Well, in this fraction, basically everything will cancel except the n plus 1. So all of these guys cancel in this fraction except the n plus 1. What you end up with is just 1 over n plus 1. We're going to use this little fact here. N factorial over n plus 1 factorial ends up just being 1 over n plus 1, because they all cancel except for one of the n plus 1s at the bottom. All right, anyway, let's do this. I want to know, where does it converge? And to answer this question, we're going to use the ratio test. And I hope you remember the ratio test. The ratio test involves doing the lim n goes to infinity of a n plus 1 divided by a n, right? This is what we talked about last time. And this limit, we call this L. L. And the ratio test says if L is less than 1, then the thing converges. If L is greater than 1, then it diverges. And if L equals 1, then you don't know. Then it's inconclusive. All right. So let's see if we can find the L. The L will depend on x, and then that will tell us if it's less than 1, it or whatever. It'll tell us when it converges in terms of x. So let's do it. You got to plug in. I lost my formula up there. Plug in for the a n plus 1 and the a n. So I go lim n goes to infinity. Okay, a n plus 1, you got to read that formula up at the top there and use n plus 1 in place of n. So this is going to be, put my absolute values, it's going to be a big old fraction. Minus 1 to the n plus 1, x to the power 2 n plus 1. Make sure you are reading the formula and just replacing the x, replacing the n with the n plus 1 everywhere. All right, divided by 2. So I'm up here. I don't know if I don't think I have a little pointer in this app. I'm looking up here now on the bottom, replacing n's with n plus 1s. Whoa, whoa, whoa. Sorry, I'm still learning here. Replacing n's with n plus 1s. Okay, 2. So it's going to be 2 to the power 2, parentheses n plus 1. And then n factorial becomes n plus 1 factorial squared, like that. All right? All of that is a n plus 1. And then I got to go divided by a n. And I'm going to copy. I have to scroll it so you're not going to see it anymore. But I'm going to copy exactly what's inside the sum there on the bottom here. So a n is minus 1 to the n, x to the power 2n divided by 2 to the 2n, n factorial squared. All right? This is my an plus 1 divided by an. All right, we got to simplify. I'm going to rewrite the division as a multiplication of the reciprocal like I always do. So this is going to be lim n goes to infinity. All right, we keep the absolute value signs, but it's minus 1 to the n plus 1. X to the... Can I distribute there? It said x to the 2 parentheses n plus 1. I'm going to make it x to the 2n plus 2, right? Divided by 2, same thing, 2n plus 2. And then n plus 1 factorial squared. Okay, times, that was the numerator, and then I'm going to go times the reciprocal of the denominator. It's going to be 2 to the 2n, n factorial squared over minus 1 to the n, x to the 2n. All right. Okay. Any thoughts so far? I hope everybody's, it's just a big nasty thing we are trying to simplify. Let's keep it going. What can we simplify here? I'm going to try and put all the similar looking things together like we usually do. First of all, the absolute values. What's going to be the effect of the absolute values? Well, we have. Can you see when I do that? Maybe that looks kind of crazy. We have absolute value signs that are going to, the effect of them is they're going to cancel out this part and this part, right? The minus ones. I don't like that. Ooh, do I get more? Sorry, I'm playing around here. I don't think I get a pointer. The absolute values have the effect of killing the minus ones. You have to look at what else are they going to have an effect on. How about this power of 2? That has no, the absolute value won't affect that because that's already going to be positive. So the power of 2. Same goes with the factorial parts. They are already positive. What about x? Actually, we don't know if x is positive or negative. So the absolute value sign will have an effect on the x. It will just turn into whatever absolute value of x is. And there's no way to simplify that away. So what we end up with is same old lim. I'm going to put things together, the similar things. So the 2's look like 2 to the 2n over 2 to the 2n plus 2. And then we have the factorials. Looks like n factorial squared over n plus 1 factorial squared. And then I have the x's. Now the minus ones, I said they will be killed by the absolute value signs. The x's turn into absolute value x. And this will be to the power 2n plus 2 over absolute value x to the 2n. All right. So when you take the absolute value, it needs to stay wrapped around the x because we don't know if the x is positive or negative. But all the other stuff in there was positive except for the minus ones to the ends, which just go away. All right. What's next? Continue simplifying here. Lim n goes to infinity. What do you say? Can someone tell me what do we get when we simplify those 2's? 2 to the 2n over 2 to the 2n plus 2. This is similar to some stuff we did last time. Yeah, all those 2's will cancel except for 2 to the 2 will remain on the bottom, right? The bottom has 2 extra factors of 2. So this first part turns into 1 over 2 to the 2. All the other 2's in those products will cancel. Next, what about the factorials? Okay, these are squared, so I'm going to write it like this, n factorial over n plus 1 factorial, and then another one, right? This is the simplest way to see what's going on with those. And then those will simplify. Each one of those is equal to 1 over n plus 1. So maybe I'll write that as another step, even though we're not quite done. So this will be 1/4 and then 1 over n plus 1, right? And then another 1 over n plus 1. Sorry. Come on now. I gotta get used to don't touch the other part of the screen. All right, each of those factorials, this is what we talked about before. When you divide a factorial by another factorial, almost everything cancels. Okay, and what about the x's? The x's actually are going to act similarly to the 2's. Up top, we have this fraction here. On the top, we have 2n plus 2 factors of x. On the bottom, we have only 2n. They will all cancel except there'll be 2 left over on the top, right? So it's going to be just absolute value x squared. 2 of those factors left over, and they're both in the numerator. All right, so absolute value x squared. Okay, so just rewriting this in a nicer way. What I'm looking at here is 1/4 times, I'll write it this way, absolute value x squared over n plus 1. All right. And we're supposed to be taking the limit. Now, finally, we can do the limit here. What happens to this? It's a fraction. The 1/4 doesn't really matter. What happens to the fraction when n goes to infinity? The answer is the fraction becomes 0, right? We don't know what the x is, but it doesn't matter. Whatever the numerator of that is, the fraction is going to become 0 when the n goes to infinity. And the 1/4, I mean, it's going to end up looking like 1/4 times 0, which is 0. I'll write it this way, 1/4 times 0, which is... yes, thank you. It's n plus 1 squared, which doesn't really matter, but you're still going to get 0. The denominator will still become infinite in this fraction. Thank you for that. All right, we got 0. Anyway, what does all this mean? So L equals 0, so it converges. Actually, the question here was, for which x does it converge? And in fact, what we've determined is that it doesn't matter what the x is. It always converges, right? So this is an example of a power series in which it converges for every value of x. So this power series converges for all x. All right, sometimes that is the answer. Power series converges for all x. All right, this was I would say, algebraically complicated, a lot of fractions and canceling involved, but we ended up with L equals 0, which means it converges for all x. Any thoughts about that one? We got more where that came from, although that's a little more complicated than most of the ones we're going to do. Can you do the most complicated one first at 9 a.m.? Maybe. I don't know. I can. Let's say a little bit more about power series. All the examples that we've been talking about look like something like this: some constant plus. This is the general format of a power series, right? This is what a power series looks like with various coefficients in front of them. Actually, there is another sort of slight variation type of power series that we're going to talk about a lot. This one, so this is a power series. The word that's used for this type is centered at 0. Centered at 0. And you can make a power series that is centered at some other number, and I'll say it'll take us a little bit to understand why should that be called centered at 0. But let me just tell you, I will say a power series centered. Come on now, my handwriting. Centered at some other number a. For a number a is something that looks like this. It still has a constant, but then instead of powers of x, it's powers of x minus a. It turns out for certain situations, it is useful to do a power series where instead of powers of x, you have powers of a. And we're going to see some examples of why that would be useful and also why that should be called centered at a. The idea is in one like this, it is centered at 0 because if you plug x equals 0 in, then all these things go away and you just end up with the constant term. Whereas this one is centered at a. It sort of means that when you plug x equals a in, then all of the variable terms become zeros, and all you get is the constant term. But that's a vague idea. We're going to say more, hopefully by the end today, about why this word centered is used. But anyway, this is just the terminology. Let's look at one like that, which is centered, which is not centered at 0, and talk about its convergence. So how about something like the sum x minus 2 to the n over n plus 4. So this one is centered at 2, right? Centered at whatever means the terms have powers of x minus a, whatever the a is. In this case, the a is 2. This is a power series centered at 2. And all right, let's try and do the same old thing about tell me where, for which x does it converge? We're going to do the ratio test. All right, we'll do the ratio test. It is lim n goes to infinity, absolute value an plus 1 over an. The absolute values really don't matter in this case because everything that you see will be positive, apart from the x. As always, we don't know what the x is, and in this case, that means actually we don't know what x minus 2 is, if it's positive or negative. So we are going to have to maintain the absolute values for that one. But anyway, what do we get? Sorry. Plug in to the an plus 1s and the an's. Would you mind if I just write it immediately using the reciprocals rather than writing this giant fraction and then splitting it out into multiplication with reciprocal? I find it easier to just immediately write the reciprocals. Okay, absolute value. An plus 1 first will be x minus 2 to the power n plus 1 divided by n plus 1 plus 4, right? You got to insert, go up to the original formula up here and replace everywhere you see n, you replace it with n plus 1. That's what I just did down there. All right, and then times, I'm going to multiply times the reciprocal of an, exactly like it's written. So that would be n plus 4 over x minus 2 to the n. All right, this is the thing that I'm supposed to be finding the limit of. All right, let's gather things together in a convenient way, cancel some stuff out maybe, and then take the limit. What do we get? We get lim n goes to infinity. Okay, first of all, the absolute values, they have no effect on the n plus 4s or whatever, because those are going to be positive. They do have to stick around with the x's. So when I simplify away the absolute values and also put stuff together, I'm going to have n plus 4 over n plus 5. The n plus 5 comes from this denominator here. You add it up, you get n plus 5, right? Put those together. And then the x's, I have absolute value x minus 2 to the n plus 1 over, painful, absolute value x minus 2 to the n, all right? I gathered those x minus 2 to the powers, whatever, put them together and put the absolute values, because that's how we got to do it. All right, and now we cancel if we can. We can. These guys over here, x minus 2 to the n plus 1 over x minus 2 to the n, they all cancel except leaving one extra in the numerator. So it's going to be lim n goes to infinity, n plus 4 over n plus 5 times absolute value x minus 2, right? There was one factor of those left over in the numerator. Okay, what's the limit then? We've simplified all the way. You can take the limit. As n goes to infinity, the x minus 2 part will just stay like it is. As n goes to infinity, what happens to this fraction? Well, we do our usual trick with the fractions. I'm going to divide through by n on the top and the bottom. It'll say 1 plus 4 over n divided by 1 plus 5 over n. And then when I take the limit there, I keep on jumping to the next page, sorry. When I take the limit there, it becomes just that fraction part, just its limit is just 1. So it's just 1 times absolute value x minus 2. All right, so in conclusion, the L is absolute value x minus 2, right? We have computed the limit of the ratio. What does this mean? You have to remind yourself of the question we are trying to answer here is, for which x does this converge? Well, the convergence is determined by this L, so it converges when L is less than 1, right? This is the rule for the ratio test. It converges when L is less than 1. I will say i.e. converges when x minus 2 in absolute value is less than 1. And it diverges when the L is greater than 1. So it diverges when absolute value x minus 2 is greater than 1. All right? Can we say, so this is the answer, right? I mean, I asked you to say for which x values does it converge and for which x values does it diverge. We can actually kind of illustrate this in a different way. The convergence, in this example, oh, actually, sorry, before I say this, I'm not going to try to illustrate it in a different way. What about when absolute value x minus 2 equals 1? Actually, we have not yet determined if it converges or not in that situation. What about absolute value x minus 2 equals 1? Well, using the ratio test is inconclusive when L equals 1. So actually this question cannot be answered by the ratio test. There are actually two different possibilities for this. Can we solve for x here? What about when x minus 2 in absolute value equals 1? This means the way to think of this is the distance. The distance from x to 2, isn't it? That's how it is most convenient to think of that thing, absolute value x minus 2. At least at this point, it's helpful to think of this as the distance from x to 2. And what if the distance from x to 2 is 1? So if this equals 1, then there are actually two possibilities for what x could be in that case, right? We're saying 2 is here, and x is one unit away from 2. It's either 1 or 3, right? Then x equals 1 or x equals 3. And these cases, we need to check by other methods, right? This is the L equals 1 case, in which case the ratio test cannot be used, and you need to just do it some other way. So let's check these specific cases individually. And you're not allowed to use the ratio test. You have to do it some other way. You'll see actually these special cases usually tend to be easy to do anyway. Whoa, sorry. No. All right, let's do x equals 3 first. So if we are looking only at x equals 3, then the series says, do you remember the formula for the series? It was x minus 2 to the n over n plus 4, right? But if x equals 3, then this is actually, 3 minus 2 to the n over n plus 4. And that is, of course, 3 minus 2 is 1. 1 to the n is just 1. So this is all just going to be the sum of 1 over n plus 4. All right? So does it converge or not? That's our question here. Anybody have a thought about this? This, of course, if you wrote out the terms, would be 1, I guess, starting with 1. What do you think? Does this converge or diverge? Sorry, it's been a while since I asked your opinion about something. I do value your opinion. Looks like it would converge. Any other opinions? I value all opinions. Actually, this diverges. It's because this one, this is, if you want to go through the details here, which I don't really, you could use the comparison test. This one is pretty much the same as, I'll say almost the same as this. Right, the only difference would be these ones on the front, right? But in terms of the limit, these would have the same properties in terms of what happens if you add them together, all of them, infinitely many of them. And this is the harmonic series, or the p series with p equal 1, which diverges, right? And so that means the other one there also diverges. The only difference is that those few fractions on the front, but the real action happens in the limit, and these both diverge. Okay, so the series, the power series, diverges for x equal 3. All right. This was the first of the two special cases. The other was x equal 1. Let's try that out. What about x equal 1? Well, in that case, I'm going to plug in x equal 1. It'll say, the series will now say 1 minus 2 to the n over n plus 4, right? And this up top will just be negative 1 to the n over n plus 4. So this, if you were to write the terms out, it would say minus a fifth plus a sixth minus a seventh plus an eighth minus, etc., right? And actually, this is something we also talked about. We talked about this right before the exam. I don't know if you remember, but this is called an alternating series because the signs go back and forth. And we had a theorem about alternating series. It does converge, provided that the individual terms get smaller every time and approach 0. And they do in this example. So this one converges by what we call the alternating series test. I don't know if you remember this. It wasn't on the test, and it hasn't been on the homework yet, so maybe you forgot about it. But the alternating series test, it says if you have an alternating series, which this is, the signs alternate each term, it converges when b, so the theorem was that bn has to be, bn plus 1 has to be less than or equal to bn. That is, each term is smaller than the previous one. If the b was just the thing without the sign on it, and also that the bn's, the lim of the bn's is 0. All right, but both of those things are true of this series that we're talking about right here. So this one does converge by the alternating series test. Okay, can we now summarize for which values does it converge and diverge? All right, let me just refresh our memory. We said it converges for absolute value x minus 2 less than 1. Also converges for x equals, this last one we just talked about. It also converges for x equals 1. It diverges for x equals 3, and also diverges when x minus 2 is greater than 1 in absolute value. All right. And this covers all possibilities for what x could be. For every possible x, we have determined whether it converges or diverges. And now I will say another way of visualizing this is as an interval of x values. If I look at x values here, when x minus 2 is less than 1 in absolute value, this means the distance from x to 2 is less than 1. It converges. So that if I put 2 here, and these are, oh, come on now. No. Sorry. If I put 2 in the middle here and say this is 3 and this is 1 here, it converges for all the values in the middle there, right? All values between 1 and 3. And it also converges when x actually equals 1, but it diverges when x equals 3. So if I wanted to indicate where does it converge, it would be like it does converge at x equals 1 and at all of these values in between. It does not converge at x equals 3. That's why I'm making that little empty circle there. All right, this is the convergence here. It converges in here. All right, and in fact, this makes an interval, right? It's the interval from 1 to 3, which includes 1 but does not include 3. All right, and there's a name for this. This is called the interval of convergence. Oops. So this is called the interval of convergence. In this example is 1 to 3. Remember how you write intervals with the brackets? The closed bracket means I do include the endpoint on 1, and then the sort of the roundy bracket on the right means I do not include the endpoint at 3. All right. So in this case, the interval of convergence is from 1 to 3. And I will have you notice that 2 is right in the middle of that interval. All right. It is the center of that interval. In fact, this is why this is called a power series centered at 2. It turns out that every power series has an interval of convergence, and the center of that interval will always be whatever the sort of the center, it's called the center of the power series. In this case, it is 2. This is called the interval of convergence. We also often discuss the radius of convergence is sort of, if you don't mind me using the term radius, it's the radius of this interval, meaning from the middle out to the edge, how wide is the interval? And the answer is 1 in this example, right? The radius of convergence in this case is called 1. That's because that interval from its middle to the edge is distance 1. That's the radius of the interval. Usually we don't use the word radius for an interval, but in this case we do. It's called the radius of convergence. I think of 2 is the center of the interval, and the width of the interval measured from the center is 1. That's what the radius of convergence means. The width of the interval from the center is 1. All right. This is called, sorry, I'm off the screen. This is called the radius of convergence. It's the width of the interval measured from the center. All right. There's a theorem. Actually, this is, I don't know if it might seem like kind of a coincidence. In this particular example, it so happens that the convergence occurred in an interval. But actually, this is always the case. This is a theorem. I'm not going to try to describe why this theorem is true, but this is an important theorem about power series, and it basically says that there is always, no matter what the series is, the convergence happens in an interval called the interval of convergence, and there is a radius of convergence. So here's what the theorem says. It says if f of x is a power series centered at some value, some number a, then the convergence always occurs in some interval around a, in terms of some radius of convergence. So I'm going to say then there is a radius of convergence, which we will usually write as a capital R. This radius of convergence is very closely related to the L from the ratio test, as we'll see when we do more examples. The radius of convergence, R, such that, what's the important property of the radius of convergence? It is that f of x converges when x minus a is less than the radius of convergence, and diverges when x minus a is greater than the radius of convergence. All right. So when x is within this radius of the number a, it converges, and when x is further than that radius, then it diverges. This is called the radius of convergence, and it is a fact. So this theorem is just saying that every power series has a specific radius of convergence. All right. Let me just say, this is sort of parenthetically, what I just wrote doesn't make a lot of sense if r is 0. So I will say when r is 0, first of all, r has to be positive or 0. R being negative doesn't make sense at all for these, because then these things can never be true. But it is possible that r is 0. In that case, then f of x converges only at x equal a. All right, that's how you interpret. If the radius is actually 0, it means that that center point is the only place where it converges. And when r is infinite, it is sometimes possible that the radius of convergence is infinite. And that just means that f of x always converges for every x. And we actually saw an example, like that very first example we did today was one in which always converged, right? The Bessel function, whatever. Okay, we got 5 minutes. I think it's enough time to try one more example. I give you, this is like going to be a big thing that we do. I give you a series. You tell me what the radius of convergence is. That will tell you for which x values it converges and for which x values it diverges. Here is an example to finish us off. 2 to the n, x to the n over square root of n. Find the radius of convergence. All right. Now, there isn't a formula for the radius of convergence. So when I say find the radius of convergence, you can't just like plug something in and find the r. The radius of convergence in all the examples that we do is going to be found by doing the ratio test. So I'm going to say this, and you will see why. This is closely related, although again there's not really a formula, but it's closely related to the L from the ratio test. All right, so do the ratio test to find a formula for the L in terms of x. Let's do it, because we've only got a few minutes. I do the ratio test. It's going to say lim n goes to infinity, absolute value, a n plus 1 over a n. All right. I'm just going to jump straight to the multiplying the reciprocals. So a n plus 1 looks like 2 to the n plus 1, x to the n plus 1 over square root n plus 1. We just go through and replace all the n's with n plus 1s. And then times an is the exact thing as written, but I'm going to take the reciprocal. So root n on top, 2 to the n, x to the n. All right, in absolute values. Let's do what we do, gather together the things that look similar. Still keep the absolute values for now. Let's put the 2's. 2 to the n plus 1 over 2 to the n, all right? And then times, how about the square root things? Sorry. The square root things, root n over root n plus 1. And then the x things, x to the n plus 1 over x to the n. All right. Let's talk about absolute values. What's the effect of the absolute values? Actually, the absolute values have no effect here because those are positive numbers, 2 to the n. They also have no effect here because square roots are positives, so they only affect the x's. And so to deal with the absolute value signs, we can just basically push them all the way in to the x's. So it's just 2 to the n plus 1 over 2 to the n. Root n. Would you mind, instead of roots, I'm going to use 1/2 powers. And since it's on the top and the bottom, I can just write this. N over n plus 1 to the 1/2. That's helpful when you're doing the limit. And then finally, absolute value x to the n plus 1 over absolute value x to the n. All right? Those absolute value signs, they have no effect on the 2's or the roots, but they do have an effect on the x's, the powers of x's, and they can just push all the way into the x's. All right, simplify. We're getting there. 2 to the n plus 1 over 2 to the n. All the 2's cancel except you get 1 left over in the numerator, so that's going to be a 2. The next thing, you can't do much to cancel, although for the sake of taking the limit, I'm going to divide out by n like we usually do, on the top and the bottom. And then finally the end. Also, these mostly cancel. We have many x's on top, x to the n on the bottom. There's an extra 1 on top, right? So we end up with just absolute value x. And then finally, taking the limit, that fraction right in the middle becomes 1, and everything else just stays like it is because there are no n's anywhere else. So when I do the limit, it's just going to be 2 times, I mean, if I want to write it out, it's like that, right? To absolute value x is the limit. Okay, so when I did the ratio test, L is to absolute value x, and I say it converges when L is greater than 1, right? To absolute value x, sorry, less than 1. Right, converges when L is less than 1. And then this you can solve for absolute value x, i.e. absolute value x less than 1/2. And this is where the radius of convergence comes from. Anyway, diverges, although it's not so important for this particular problem. Come on now. Diverges when 2 absolute value x is greater than 1. But we don't really care. This is what's important. The absolute value of x being less than 1/2 is when it converges. You know, if you want to indicate that like an interval, it looks like this, right? Going up to 1/2 and going down to -1/2. This is the convergence. And so what's the radius of convergence? It's just this number, the 1/2 there. That is the radius of convergence. So the radius of convergence, r, is 1/2. It's the, you know, the distance from the middle out to the edge. All right. And this is basically how these examples will always work out. You find the L, you get some multiple of absolute value x, or if it's not centered at 0, it might be absolute value like x minus 1 or something. And then basically that number right there, this number, ends up being the reciprocal of the ratio of convergence, because you have to divide by that. This is how it's always going to work out. All right, and that'll do it for our time today. Sorry we had to do it on Zoom, but I look forward to seeing you all in person on Friday. Somebody asked me, sorry I forgot to mention this in class yesterday. We don't have homework due today because we only had one class last week. We're just going to gather it all together. And that means we do not have a quiz on Friday. So just normal class on Friday, no quiz. All right, see you then. Have a good one.